get started. So we're going to do is talk about random variable. Okay. So what is random variable? Okay. What's random variable? Random variable is a natural thing you would consider when you consider outcome of a random experiment. Okay. We know experiment like tossing a coin, rolling a die, right? They come up with an outcome, right? We are assigning probability to those outcomes, right? And a lot of time these outcomes are very complicated, right? It's not just have a coin, a die in the real world. There's a lot of details to record, right? And sometimes you don't really care some of details of outcome. For example, you may not care, say you roll a die many times, you don't probably not care the exact number each rolling, right? Maybe care about some of the numbers, right? Or you don't really care about is it first time head or second time head, as long as number head the same, right? So you just simplify the outcome of the sample space. So one way to do it is to consider random variable, use a number to represent the outcome of the sample space, okay? And the number that used to represent the outcome of sample space are called random variable, okay? So that's why it's a function or mapping that map outcome to number. So a random variable is a, from the sample space, there's an outcome, right? And then we are mapped to a number. And the reason why we want to use this is because of we know how to use function, okay? We know how to describe numbers, okay? That makes our life easier. Okay. Is that okay? And can you see the screen? Yes. So here we actually in the textbook there have two chapters, one called Discrete random variable and Continuous random variable. We combine them together in the same slides because I don't see the reason why to take it out. They're very similar except the tools we use. For discrete, here the number of outcomes of sample space is finite, but of course, to be more technically correct, to be countable infinite. But basically, just like you can count them 1, 2, 3, 4, 5, but this also includes infinity, right? Because you need not have an upper bound, so it can be from 0 to infinity. Okay. Basically, you can imagine integers. Okay, integers. And probably cover in the next class, we'll call continuous random variable, which said it's not finite, basically it's infinite or countable infinite. Oh, sorry, uncountable, okay, uncountable. So usually it's a real number, right? So uncountable here means not finite, here means probably any two numbers, you can find anything in the middle, right? And for any, you can further refine it, right? For the number between anything in the middle, okay, you can also find number in the middle, okay? You can keep finding number in the middles, okay? For every two number you pick from the sample space, okay, find somewhere in the middle, okay? So that continuous. And the reason why I separate the two, because the first one, you require summation, just adding. And for continuous random variable, you require integration, okay? There are tools that's why they're divided into two. Sometimes it's better to describe it as continuous, sometimes it's better to describe discrete. And the usage of the two are basically based on the usage. And why do we need to learn these two things is because of, as you will see later, there are a lot of application that tells you that you describe the underlying random experiment, it's a discrete, it's better, sometimes quant is better. Okay, it probably will be much more clear later. But at the moment, let's remember again what's random variable. Random variable are just mapping from outcome, okay, of the random experiment to some numbers, okay? That means that, there are multiple outcomes can be mapped to the same number, okay? Just like toes and con 2 times, you just record number of heads, right? In that case, if head is converted to 2, right? If head tail or tail head is 1, tail tail is 0, okay? Just to make sure that maybe take example in the next page, okay? So suppose you toes and con once, right? Then you have the sample space is head and tail, right? Or H and T, right? And let X be the random variable, the total number of heads, okay? So basically just based on number of head, you map to a number, okay? So if the outcome is head, then we will say X equal to 1. If number of tail, X equals 0, right? So if you want to write technically, right? Basically random variable X, right, is head or tail, okay, is mapped to 0, 1, okay? So usually it's like, it should be X of T, right, maybe 1, X of T, right, will be 0, right? But sometimes we will omit this argument, right? So it will be X equal to 1 or X equal to 0, okay? So, but remember, random variable is a mapping from the outcome space to the number space. Okay, but anyway, it's a little bit technical, but this is what it means for the random variable. Okay, basically just you can imagine use a number to present what is happening from the random experiment. Okay, so the next one is a discrete random variable. Another one is total and con twice. Okay, here you can see the sample space expands, right? Because 2 times 2 is 4. So here we have HH, HT, TH, and TT. As I said just now, probably you don't really care about the distinction between the two, right? Because you may just care about how many heads you have, right? So in that case, this will be 2 heads. This is 1 head. This is 0 head, right? So in that case, this is X equal to 0 means TT, right? The union of these two, right, because both of them correspond X equal to 1 and X and X equal to 2, okay? So that's the idea, right? It's, again, it's a simplification of the sample space because sample space can be very complicated. You can imagine the random variables a way to simplify it. Is there any question before we talk about discrete random variable? Is that okay? Is it good? I mean, okay, good. Another example is a continuous random variable, which you allow the number to take more than discountable numbers, right? So here, the temperature, right, is about the absolute 0. Then any temperature actually is feasible, right? Anything is fine, okay? Anything, you pick any numbers, anything in the middle is also, so it's continuous. Same as stock market index, right? So any number from 0 to any number is okay, okay? So you can see in this particular case, this actually the sample space is already very simplified, right? So you can imagine the sample space can be like the stock market, right? There are many stocks, right? Each stock has one number, right? And the random variable in this case, stock market index is simplifying the sample space, right? Because you can imagine the what's happening is the whole stock market, right? And the many stocks, and the stock market index is basically simplifying the overall stock market movement. Okay, I hope that's fine. Then let's get start on the discrete random variable. I hope that's okay. If you have any question, please feel free to leave your message in chat or unmute your mic and talk. Okay. What sample symbol look like? Where is that? Hui. So where is the symbol?
On the next slide.
This one?
The previous slide.
This one?
Yes. The X, and then there is a symbol looks like E.
It's R.
R and E.
This one?
Yes.
But this one? Oh, this is a real line. This real number.
Okay.
This corresponds real number line, which is this real number. Real number is 0, 1, can be 1.5. Any positive. This is a real number. You know real number?
Yes.
Okay, this is real number, and this is positive real number. Is that okay?
Okay.
Just this is standard notation in the math. Okay, thanks for asking. Yeah. Choi Lam, yeah, please ask. I have E. Where I have E? Oh, someone asked me the E. This is R. This R. Real number. Oh, this is E. Oh, you asked this. It's belong to. So this is a set notation. So we say, okay, S sample space, right? What are the sample space? Okay, the sample space means every number. This is can be called belongs to R is the set of real numbers. Okay. So what is sample space S? S is all possible numbers. That is also the real number. And we are saying that this real number must satisfy the condition where X is bigger than absolute 0. Is that okay? I guess they ask you this one. So this is a set notation that belongs to. So because this is a very big, is a big set collection of numbers, and this again, sample space is S is the positive number, and here is X belong to set of real number such that X is bigger than 0. So this is, you can say such that. Okay. Is that okay? So if you try to look at all the math textbook, this is a very standard notation. It's not something invented by me, but if you try to look at those, but if you feel confusing for your case, you can just usually can ignore this one. It doesn't really matter because usually talk about real number already, so it's not a big deal to omit that one. Is that clear? Good. If you feel confusing, you can just ignore it because usually when we number is always a real number in our application. Sometimes we will consider complex number or integer, but we don't use that notation for the moment. Okay. So I guess we should continue. Discrete random variable. Here we will talk about how to describe the discrete random variable. Okay, because this random variable has a discrete number of possible outcomes, right? Because you're mapping to integers, right? Set of integers usually. Then basically you can list them out, right? So here we use set probability of the random variable X. So the capital letter in our notation is always a random variable. Okay, this is a random variable. When I have a capital letter and the small letter is usually a real number. Okay, it's a number. Okay, a random variable equal to the number of this probability we will usually denote as P of X. Okay, sometimes some textbook use small f of X, also fine, but to make the, I think to make our life easier, we just use P, because we want to save the F for the continuous one. So when you see P is a discrete one, okay? And the cumulative probability will be f of x is a probability that x is less than x, okay? So these are two definitions. So there's nothing to explain, but just different definition. So you just know it or not knowing it. So there's nothing to worry. But for the moment, it's clear what they are. Okay, but anyway, probably still too abstract to say whether you know it. Or maybe give an example. So here I have a sample space of running die, running fair die. Okay, it's 1 up to 6. Okay, and to very naturally, your random variable is the face value of the fair die. Okay. Okay. So here already, actually, I write the number already, right? But this one actually is it's not 1. Actually, 1%. The face value of the die is 1, right? And then you naturally you have a random variable called 1, okay? Because, but we just already somehow we have to abstract from the outcome of the sample space, right? So 1 actually means the face value is 1, okay? Here I have a x can be anything from 1 to 6, right? So here I can actually represent the probability discrete function and the cumulative probability function using the table, right? Because we can list all the 6 number and the probability, right? Because it's a fair, okay? So each outcome is equally likely, right? So that's why the probability function, which is mapping from the value x, right, to the number 1 to 6, right? They're equal likely, they're all 1 over 6. Okay. The cumulative one, okay. This one is asking what's probability that is x is less than or equal to 1, so it's 1/6, right? And this, right, f of 2, right, is asking probability that x is less than or equal to 2, right? So which in this case is x is equal to 1 plus x is equal to 2. Okay? Anyone can tell me why you can write this? Okay? This is, no one want to write down. Okay, because this is axiom free, right? Because right, this is a union of x equal to 1, right? This is x equal to 1 and x equal to 2, right? Or you don't like and, then maybe union, right? And because 1 and 2 are mutually exclusive, right? So you can have the same one or two same time, right? So you can rewrite it as 1 or 2, right? So which is 1 over 6 plus 1 over 6 is 2 over 6, right? So same for the rest. Okay, is that clear? Oh, P of x, say P of 2 is just asking probability x equal to 2. Okay, and F of 2 is asking probability x less than or equal to 2. Okay, okay, so the key difference is this one. Is that okay, Trilem? This is equal, but this is less than or equal to, okay? So very good. Feel free to ask the question because sometime I may go over it too quickly, but I hope that's fine. Yeah, please feel free to ask a question. So we can actually plot this diagram. Usually that's what you do because this is like the histogram or bar chart. That is something that we want to know. And let's see the chart. Okay, so this is the probability function because they're 1, 6, right? So that's why here, right, it's 1, 6, right? But I didn't make explicit, but this is what Px is. And the discrete, so that's why there's nothing in the middle, right? So that's why this is a bar chart rather than histogram, right? There's nothing in the middle. But the other thing is to be 0, okay? So to be more accurate, so you should have this one, right? So if you, okay. So to be formal, you should be right this way, right? It's a function is equal to 1, 6 if x equal to 1, 2, up to 6, right? And 0 otherwise. Okay, so you should include this all 0 there. But I don't think it's very clear from here, but this is something that should be, right? Because the function, right? It's a real value function, so you should tell them what should be the value of this when for other, when x assume other value. But anyway, this is more technical here, but let's clear the. Is it okay? I don't think there should be any issue by just drawing the chart. So here I have write the cumulative function, but I should be more careful. It should be something like this. If I should be, so it should be like this as a step function because sorry, my bad. Okay, so it's 1, 6, sorry, this is 0. This is 0, this is 1, 6, 2, 6, up to 1, okay? The reason why we have here this here because probably f of say 1.5, right, is probability that x less than 1.5, right? But this is same as probability that is x less than 1, right? Because there's nothing between 1.5 and 1, right? Which is equal to probability x equal to 1. Okay, that's one. This is 1 over 6. Okay, so it should be like the step function. I guess that should be okay. But yeah, technically 1.5, but this is a function. So usually the function is a real value function. So you map from that one. So this is technically that you would be doing that. But for our application, that we don't need to worry about that. But this is usually when you write this function, you will be writing all possible value. So this is technically how statistic people write it. But for a business application, you write this chart, no one would complain. So that's why I leave this chart. But this is technically a step function. And this is usually what you get when you have a software package. When you draw it, they will give you this kind of style. But doesn't really matter for our application. But just let you know that you can also take the value in between. But as you have Choi Lam said, I mean, technically it will not be 1.5. Is that okay? Yeah. Okay, I hope that is all right. So let's get little bit interesting thing. Actually, you learned this from our first chapter, but this is something a little bit new in terms of probability. Okay, so remember weighted average, right? Weighted average, right? It's like if you remember, weighted average is x bar will be equal to summation of wi xi over summation of wi, right? I hope you still remember this, right? And now x can be, remember the graph before you have x, right? can have different value, maybe 1, 2, up to 6 in the example there, right? The P of X can be 1, 6, 1, 6, 1, 6, right? But can be any value. But you can see here, I can find the mean of X using P as the weight, okay? The weight. P the weight, okay? So then the weighted average, okay, of this random variable using the probability as a weight is called the expectation. Okay, that is something that on average this is a number we're expecting. Okay, so if that means if you try to guess what's the number to be there, then you will be a something in the middle. Okay, and because the sum of the weights are 1, right? So that's why this is 1. Okay, so that's why you have this expectation notation. Okay, here means summation, summing all up for every value X, okay, possible X, you times its weight. Okay, remember all the weights now sum to 1 because probability all sum to 1. Okay, and usually we denote it as mu of X or sometimes simply mu. If X is, we just have only one random variable, we just write mu. Okay, is that clear? Okay. The next thing we would be concerned ourselves is what we call the variance. Probably you know the definition, right? Is the variance, right? Is the expected, okay, square difference from mean. Okay, here is the quantity X and the difference between X and the mean and take square and expectation of that, right? Basically is what you get from the expectation, right? You take every value minus expectation and square it, but again, it's a weighted mean, it's weighted by its probability, okay? And that's we call the sigma square X. So there's nothing new, but this is a, write everything into the probability language. Is that okay? Is that okay? So these two concepts are so important that we'll be keep using that all the time. So just maybe give example. Let's see the example. It will be hopefully become more clear. So rolling die, right? You know the die, just to recall, right? Die is fair die, right? We have 6 outcome, right? 1, 2, 3, 4, 5, 6, right? P of X is 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, 1, 6, okay? And the question is expected value, right? Expected X, right? So basically, here is very clear. It's just multiply, 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 and add. Okay, so that's exactly what's going on here. All right, so it's 3.5. Okay, you can check this is right during your break later. So, and the variance of X, okay, what you're going to do is you take every value minus mean, okay, is 1 minus 3.5 square times 1 over 6, 2 minus 3.5 square times 1 over 6, and so on and so forth, okay? So until you get all the numbers and you get somewhat like this, okay? Later you can verify this is the case, okay? But I'm not going into the detail. I hope you should be able to do this computation. Okay, any question about this example? meaning of variance. Variance is, let's go back to the, so this is asking how the probability, how you can imagine this is the expectation. Expectation is asking, okay, this random variable on average what value is, right? And the value is asking how accurate is this expectation, right? Because if this is far away from every value is far away from expectation, this value will be big, right? It's measuring how that. Suppose we have two distributions, right? So suppose this. So this is one. The mean is here, right? So for this, the first case, okay, and consider the second case. The mean x bar is here, right? But using the notation is u of x, right? This mu. This is also mu. Maybe I use the y to be a little bit more easier to understand. So this is y. This is, oh, sorry. It's color blue. Y bar, right? It's mu of y. Okay, and you can easily see that the sigma x squared, okay, how it compared to sigma. Oh, sorry, this is x. This is sigma y. Okay, so can you tell me, Choi Lim, can you tell me which sigma is bigger, x or y? No, reverse. It should be x is bigger, right? Because x is more spread out. You get that, Choi? Okay, yeah, but is it clear? Yes, I recommend for those who are not there that you can look at the video before, but our class is not built on the previous. I mean, sometimes people on thesis things, so you can just try to go back and check. But I hope that's okay. Is that okay for the moment? Is that clear? It's okay. Don't worry about that because I think not everyone remember everything before, so it's okay to ask questions. So feel free to ask questions because the concept is not deep, but you need to remember. You just get it. It's not something very complicated, but just. Is that okay for this one? Any question for the example? Good. So we actually don't prove, or actually it's easy to prove, but we don't prove so that this is basically follow from the summation property or addition property, okay, adding property, right? Because remember the other day, right? Expectation, right? It's just summation x times p of x, right? It's just weighted average, right? And that means if you multiply the random variable by constant plus a constant, that you don't need to redo it again. You just a times expected of x plus b, okay? And that means that we don't need to start from scratch, okay? We just calculate a very simple value, okay? If we need more, then we just do it, okay? That simplifies the calculation a lot, okay? Later in the example, you will see in the application that this thing will be needed. Okay, we often need this later, so don't worry about that if you don't follow it. But this is this property of expectation will be needed all the time. Okay, the second one will be the expectation of two random variable. Okay, to add together, you can just rewrite as actually because they are the same because they're adding, right? So there's no you can separate them. Okay, and this A can be taken out, so that's why you can write this, and this is B. Okay, so this is following the summation, right? Because I just try to prove this. Okay, and the rest will be simple. So this will be equal to A of x, right, times probability AX, okay? But this, okay, suppose you have 1, 2, 3, 4, 5, 6, right? A is say 2, okay? So A of x is 2, 4, 6, 8, 10, 12, right? But the probability is the same, right? Because P of x is still 1, 6, right? Okay? So that's why you can write summation A of x times P of x, okay? And this A is a constant, right? So you can take it out. A summation xpx, okay? So that is equal to A expected x, okay? So this is how this proof, this is the case. You can see plus B the same idea, okay? It's linear, okay? Of course, you may not care about the proof, and we don't care about the proof, but I just showed you everything can be proven pretty easily by expectation. But I guess none of you, I mean, not none of you, but most of you don't care about the proof, but just, but we'll be using this all the time, okay? You may aware or not aware, this kind of thing is being used all the time, okay? But just give you the idea, okay? And I will talk about one more property before I go to the example, okay? And then we'll break 5 minutes. As I said, today we have a shorter break because of we have a late start. So we have two constants, A and B, and X and Y are random variables, okay? So this is a shortcut, okay? Actually, you can prove it. I guess some of you know the proof, but I'm not going to prove it. That's something not very difficult to prove. And actually, we will use it all the time when we go to regression. Okay, the last chapter, we will do the proof more carefully by then. But at the moment, let's I think chapter 6 also we also do some proof on this. But the variance, right? Remember the formula variance of x is expected x minus, okay, is the difference from the mean, and take the square and asking on average how this distance looks like, right? It's asking the distance from the mean and square it and how they look like, right? Okay. And usually the calculation, as we said, can be written as this. Okay. So what it means is, instead of calculating this complicated thing, you can calculate the mean and take the square, okay? And calculate the squared expectation, okay? What does this mean, okay? Let me give example. Say suppose, go back to the lowering a die, right? X will be 1, 2, 3, 4, 5, 6. X squared will be 1, 4, 9, 16, 25, 36, right? Then what is expected x squared, right? It's just 1 times 1, 6, because everything is 1, 6, right? So it's 4 times 1, 6, okay? Until 36 times 1 over 6, okay? You calculate this, right? And minus, this is 3.5, if you remember the example, square, you take this minus this, you'll get the same result, okay? And the reason why you would prefer this formula instead of this, right? Because computationally, this is much faster, right? You don't need to do subtraction. You just do subtracting once, okay? So that is sometimes this is preferred. And also when you derive formula, this is also easier, okay? And these two equations actually are very similar, okay? Because you take square, okay? So that's why if you have a multiply by A becomes square, okay? You can easily see it because there's square here. There's A squared, take it out, so that's why square. And why B is not changed. Intuitively, that means you move all the data from one side to the other, right? You just parallel shift everything, all right? Then the variation doesn't change, right? So suppose you have x plus 1, right? The data become 2, 3, up to 7, right? So you can see the data is not spreading out, okay? So adding any constant will not change the variance. So that's intuition, right? And if you multiply the x by some number, right? And because variance will take the square distance, right? So that's why the distance will take its square, okay? So that is the main intuition behind it, but of course you can prove it, but I guess you don't care about the proof at the moment, okay? So we'll do more proof later, but for the moment, let's take it as granted. Next is something that is interesting, x plus y, okay? And you can prove it, but we don't do it here at the moment. So it will be variant x plus variant y and 2 covariance x plus y, okay? So which means that if x and y independent, okay, that's very key, listen this carefully. If they're independent, the covariance is 0, okay, if they're independent. So the variance x plus y will be sum of their own variance if they're independent, okay? But if not, this covariance will matter, okay? And for those who learn finance, then you notice that this covariance is important, okay? Why you want to combine, how to form a portfolio, right? Why you want to invest A, invest B, right? And how to diversify your risk, right? Because variance, if you learn finance, this is a risk measure, right? Because how variate, right? And very often you want to minimize your risk, okay? How do you minimize the risk? By combining different portfolio, right? Is when something go up, right? The other thing go down, right? It will kill some of the variance, right? Just like there's some defensive stock, right? And this thing tend not to move that much or move in the reverse way, right? So they will make your portfolio not vary that much, right? Because say for some stock, you do well in the recession, some stock do well when the boom, right? So they cancel out somewhat. It will lead the reduction, right? When they cancel out, right, that means the covariance is negative, right? Because when something tend to move above the mean, the other one below the mean, right? That's what the negative covariance mean, right? So that's why the covariance is important for those who know the finance. If they're independent, right, and doesn't really matter if how the composition of them, right, doesn't really change that much about the variance. But anyway, let me give an example, then we'll break, okay? I hope that's all right. Let's have this example with a short break, okay? Now we have an application. It's a portfolio application, and this is something that probably you will be doing if you learn more finance portfolio theory. I think the finance class in 3000, they talk about all this all the time, about how to figure out what's appropriate composition of the portfolio, okay? So here I give example. Stock X, okay, have mean return of, I think, not probably, I think it's 10%. One's 10%, and the variance is 0.05, okay, and stock Y is 5% mean return, and the variance is 0.01, okay. And these two stock are independent, right? Independent would imply covariance X, Y equals 0, okay. And portfolio Z is equally divided between two stock, so it's 0.5X and 0.5Y, okay. And so what is expectation portfolio, okay? In that case, it's 0.5X and 0.5Y, right? It's half of X, half of Y, right? So using the notation formula here, this can be taken out, right? And you have expectation of X, this is E of X, okay? And this is E of Y, okay? Sorry for the E of Y, okay? and right, it's 0.5 e of x plus 0.5 e of y, okay? So that is a expected return of the portfolio, okay? And this is 7.5, okay? And here we have variance of portfolio x and y, right? And here we can see z is equal to half of x and half of y, okay? And we know the independent, okay? So that's why you can write the following is variance, okay, 0.5x plus variance of 0.5y, okay? Okay, and because of a constant multiplied by this, you can take it out, right? So that's why it's 0.5 square variance of x, okay, plus 0.5 square variance of y, okay? Variance of x is 0.05, variance of y is 0.01, okay? And you can do it, then it will give you this answer, okay? So that's how you can calculate the variance portfolio, okay, by using the formula, right? That would be save a lot of time. So that is something, if you learn finance, you often use this. Okay, let's have a break of 5 minutes. In the meantime, I answer the question you might have. So let's resume to save time. Let's resume at 5 minutes after. So it's 9:41. Okay, let's resume of that. In the meantime, I answer the question you might have. Yes, have a break. Break. So feel free to ask me a question. Yeah, question time. It's your break time, but it's my question time. Someone asked me, do we have exercise? So the question, someone asked me, every exercise, every chapter, we will have homework assignment that we will give you some exercise. So I hope that will be helpful. Does it solve your question? Kai Cheng is okay to be, if you're late for technical problem, you can view the video we upload later. There's no problem. Yeah, no problem. As long as you can just watch the video to see. And also we will have I have another section in the next class. So if you really want to look at the real time, probably you can continue. I can give the link, but usually you can just watch the video if you have anything. Yeah, but we just cover up to slide 15. Or you have any particular thing to ask me? I can quickly go over again. So just Kai Chang, because basically what we cover so far is just talking about, let me clean the screen a little bit quickly to go over that with you. So basically what we have covered up to the break is just like we introduced what's random variable, which is then mapping from outcome to numbers, okay? It's basically say suppose you have a head or tail, we just match to x equal to 1 or 0. If you twice, it can be mapped to 0, 1, or 2, right? The reason why I do this is we've told many times, then sometimes we don't want to keep track of all the outcomes, but instead we keep track of 1, 2, or 0, right? Because if you toast 100 times, right, then the sample space expands crazy, right? Because it's 2 to the power 100, right? So that's why, but if you random variable, it's just 100 number. That is much easier to describe and handle. And we just talk about how to describe a discrete random variable. That's the goal of today. We have two things, what's called probability discrete function and cumulative probability function, okay? Which is x equal to some number and x is less than equal to some number, okay? And you can write down in table form, or you can draw a picture. And then next you talk about variance and expectation. These two are the most basic thing. Here, actually, when you talk about continuous random variable, they become integration. But this is how these two are important measure for probability, discrete probability. And here I teach you, I talk about the some property of expectation, okay? Because linear, so that's why in this way, variance is square, so that's why another different thing. Okay, so that is what we cover up to now. So before the end of the break, someone asked me there's an assignment. The assignment, as we know, that would be only the first assignment is assignment 1. You can check announcement on the blackboard, which said you need to collect your own data and create one-page poster or one-page summary, and you make a short 1-minute video to describe your main outcomes. Okay, this is an assignment, and it will due, I think, it's 16th of October, because I know some of you are late to this class, so that's why the deadline is longer than usual.
All right. Hello, Professor.
Yes.
Good morning. I'm actually Choi Lam. I'm new to this class.
Yes.
So I was wondering what kind of homework did I miss that counts for?
You didn't meet any homework, yeah.
Right. So the assignment would be due on October the 16th.
Yes. That's the first homework. Yes.
All right. But I saw that some homework has been posted on Blackboard.
There's only one homework there.
Okay.
There's only one homework there.
Okay, thank you.
I'll just describe that one. Yeah.
Okay, thank you very much.
You can go back. You can go back to check the Blackboard and see.
Okay, thank you.
One homework, but you're still confused, you can just email me. I try to clarify. But
okay, sure.
I think the Blackboard is pretty clear. There's only one homework now.
Okay.
Yes.
Okay. If I have any questions, I'll just email you privately.
Yeah,
thank you.
Yeah,
thank
no
you.
problem.
Thank you.
Or you can stay up to. I will be staying up after the class. You can ask questions back.
Okay. Thank you.
Have problem about the homework.
Thank you.
But there's only one homework so far.
Okay.
Okay.
Thank you. Thank you.
Any question? Quiz 1 or quiz 2? For those who add this class late, doesn't really matter. Because it's just attendance checking for that one. So if you miss, you can just miss. Don't worry about that. The answer question? Yeah, you don't have to worry about that part. If you add this class late, you will not be anything there. Okay. Any question? Any further question? If no, then we go to talk about some. So I get back the video so that continue. Sorry for the short break today because of the traffic jam. So let's talk about the common discrete distribution. Okay, so you will see today we talk about quite a few. Hopefully we can finish all of them today, but if not, we will leave it to the next class. But hopefully we can finish all. So there will be a uniform, binomial, Poisson, and hypergeometric. Okay. So why we care about this? Because these are usually coming from actual application. They have a very useful meaning. Okay. Let's see one by one, and then you will appreciate why we want to learn this. Okay. And their particular formula that will be very useful, turn out to be. Okay. So the first one is uniform distribution. Okay, there's something they're useful when using the lottery or gambling or random sampling, okay? So that means each outcome is equally likely, okay? And here is support. Support means you can see this is a idea of the sample space, right? So all possible outcome. And support is basically saying the all possible value for this random variable, okay? And that means only for these values they're possible, okay? That's x1 up to xn, okay? In the case of rolling a die, will be 1 to 6, right? But this need not be number, right? Maybe a fair con, a what, but at the end of the day, because we're mapping to number, so these are the number, but need not be 1 to 6, right? Can be 2 to 7, can be any number, okay? But what it said is each one is equally likely, okay? So that's why it's 1 over n, okay? So this is the most basic one, okay? Tossing a coin, rolling a die, or randomly pick up certain thing is always 1 over n. Okay, is that clear? Is that clear for this one? Okay, so and if you have x1 to 5, then everything is if you try to draw. So this should be I should be more careful. This should be big P. So this should be big P instead of small p, because the way I use the notation should be the big P. Should be the big P, sorry, should be the big P. So is for this case, right, 1 to 5 is 1 over 5, right? If they're 3, then it's 1 over 3, okay? So that's the way you try to draw the uniform, okay? And this is something I don't think this is worth any discussion, because this is something that's most basic one, okay? If you believe that this is a fair die or fair random event, then there was something happening, okay? And this is common, okay? There's nothing to this too much to discuss, but there's something more to discuss. Is what we call the Bernoulli distribution, okay? So as you can see, his name suggests Bernoulli is a guy, right? He's a mathematician, okay? And he started this probability theory, so that's why he started to study this, so that's why we have that first. So this is just considered an experiment, okay? With two outcomes, either it fail or success, okay? Basically, outcome, either it success or failure, okay? And with probability P is going to success, 1 minus P is going to fail, okay? So that is the idea. And we call success, we will say x equal to 1 and failure, x equal to 0, okay? Is that clear for this one? Okay? And that means probability p equal to x, right, is p equal to 0, so equal to p, probability that x equal to 1 is 1 minus p, right? And just like the support is x and 0 and 1 means what are the possible value of the random variable, okay? And here you can combine these two very interestingly. I always feel very surprising how you can write this p of 1 minus p into one formula. Indeed, you can write it in this way, okay? Very funny. So probability, this probability function, p, okay? Or if you write p of x, okay, the same as p of x, okay, is equal to the small p raised to the power x, 1 minus p raised 1 minus to x, okay? X can only be 1 or 0, okay? Just remember 1 or 0, okay? Cannot be any other numbers, okay? So in this case, if x equal to 1, right, would be p1, 1 minus p, 1 minus 1, right? So this is raised to the power 0, right? So this is p times 1 minus p raised to the power 0, right? Anything raised to the power 0 is 1, right? So that's why it's p. Okay? So same for when x equals 0, right? Would be p0, 1 minus p, 1 minus 0, that gives you 1 minus p, okay? So I always find this is amazing how the math can combine these two in the one formula, okay? But anyway, later you will see this writing actually is very natural. At the beginning now you can see it's very weird, but sooner or later you'll find this. I'm gonna talk about the next item, then you see this is very intuitive, okay? So this is the basic thing. You toss a coin, run an experiment, and with binary outcome, okay? So now we want to say, we'll prove it soon, but the mean is P, the variance is P times 1 minus P, okay? So this is rather interesting because if you recall the math you learn, right, this, you can draw P over the variance of X, right? This is 0, this is 1, this is, actually this is shape, right? Right, this is 1/4, right? This is a standard thing you expect, right? Use the variance is highest when P is is at 1/2, right? It's closer to the 1/2, then it's more likely to have higher variance, right? Why this is intuitively right? Because of the fact that if P, imagine this, if P are either 0 or 1, or close to 0 to 1, okay? Then when you toss a coin, it's very unfair coin, right? Either you have head or tail all the time, right? That means that you don't have much variability, right? Because variance measuring how variability of the thing is, right? But when P is close to 1/2, then you don't really know head or tail, right? So that means that it's further away because the expectation is 1/2, right? Then all the time you have head or tail, then the variance is large. I hope this gives you the intuitive idea why the variance like this, but of course we can prove it. There's nothing deep here, but any question before we proceed to the next slide? Is it okay for the binomial thing? Is that clear? Is it okay? Let's clean the slides. Okay, let's go to the next one. So here we have something very simple. If this is fair thing, right? P equal to 1/2, right? It's 1/2 here, right? And P is equal to 0.3, right? So, oh, sorry. So this is 3/10. This is 7/10, right? So because this represents to probability that equal to X equal to 1, okay? So that's the case. And we try to give you the proof of why the mean is P and the variance is what P times 1 is P, okay? So expectation, okay, is X times P of X, right? And the two value, either 0 or 1, and 0 is probability 1 minus P, and 1 is probability P, right? So that's why this is 0, and this is P. Okay? Now calculate the variance. Is X minus its expectation and take square and weighted by probability, right? So the first is either 0 or 1, right? The mean is P, okay? This is, remember this P are the expected value of X, okay? And this is probability that X equal to 0, right? Sorry. Okay. X equal to 0, okay? And this is probability that X equal to 1, right? And you will see, okay, this is P squared 1 minus P, okay? And this is 1 minus P square P, right? And here I can able to take myself common factor, right? P times minus P because they both have that. And then with P plus 1 minus P, okay? And cancel out, it's 1. So it's P times 1 minus P, okay? Is that clear how we get the answer? Is that okay? Good. Now, once we have this, we will have, is that okay? Okay, so that's why we have the variance. Now, the next thing is to repeat the binomial trial n times independently, okay? That's something we commonly use. This one is binomial distribution, okay? That related, later you will see we have a we relate to the combination, okay? That is what we learned in the last class, the NCR, okay? Of n object, we pick R objects, which we don't care the order, okay? And here we have n repeating the independent binomial trials n times, and each time with a separate p, okay? And the random variable is how many success we have, okay? We will be n times, right? We may have no success or with n success, right? Just you can imagine that the toss a coin, okay? N times, okay? In how many times you have a tail, suppose tail success, okay? You can have 0 up to n, okay? And you can easily see that they're not equally likely, all right? So the probability function, there's actually p of x, right? Is what, okay? It will be, okay? First, p raised to the power x, okay? Because we want x success, and we want n minus x value. That's 1 minus p raised to the power n minus x. Okay? So this is say you have x success, okay, and n minus x value. Okay, you have this. Okay, suppose the first x success and the next n minus x is value, right? So it will be success, 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 x time, right? And value, 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 n minus x time, right? So that's because the join, right? So you just multiply, okay? But there are many ways to organize this, right? You can have all the success at the below, right? At the end, right? So fail, 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 and then fail, and then success, 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 and then success, right? You can have this. Right? And the question is how many different ways of organizing this? Okay, how can I organize this? The answer is NCX. Okay. Why that's the case? Okay. The reason is rather simple. Okay. It just consider you have 1 up to n number. Okay. And you would be calling this outcome, right, will be 1 up to x. Is it just drawing this balls, right? 1 up to x, okay? Then we represent first one is x, okay? If you draw the outcome, any number, say 1, 2, 4, right? And that will be saying this corresponds to success, success, fail, success, and so on and so forth, okay? So that's why you have NCX, okay? Because from out of n trial, okay, you want x of that, okay? So there are all different ways you can reorder this success and failure. Okay, Of course, if you don't fully follow, it doesn't really matter. You can take this as given. Okay, this is something that we'll be using. Okay, I guess no one would ask you how do we derive it, but you can. The important part is this is taken as given. Okay, what we're trying to prove is we prove this too. Okay, if you don't follow this, doesn't really matter, but this is something. But of course, you should be able to derive this from the first principle. Okay, just let me repeat what it means. Okay, here is an ordered probability, right? Because first have x success, and then you have n minus x value, right? This is the probability. But how many ways you can organize this failure and success, right? Because of n trial, you have x success, right? You can have the first success, second success, and the fourth success, right? You are trying to take out x balls, right? If you consider taking out the ball as success, right? You can consider there's an n number. Each number represents a trial. How many ways you can take out x numbers, right? Take out the number means that one success. So that's why it's NCX. Okay, I hope that's clear. And then we'll try to prove the mean is NP and the variance is NP times 1 minus P. But before I prove it, is it clear what we are doing now? Okay, is there any question? Question? Okay, good. So let's visualize what we have here. You can see if P is half, okay, you will see the red one is rather symmetry, right? It's symmetric, okay? If P is rather small, right, it's less likely to be successful, right? So you can see this is will be skewed to the right, okay? If P, you can imagine if another one that is green color, right? P is 0.7, they should expect something like this happening. Okay, so if P is half, then it will be more symmetric. Okay, but for the moment, this is the graph looks like. Okay, so let's give an example. Okay, this example will be something very often you will seeing this. Okay, the question is following. So a restaurant owner, okay, have 30% people like spicy food. Okay, the question is, what's probability out of the 5 randomly chosen customer, 2 of them like spicy food? Okay, so basically what you're doing is with a large sample, right? That basically 30% like spicy food, right? And 70%, right, doesn't like spicy food. Okay, and the question is you try to going to draw 5 people here, okay, 5 people, okay, and randomly chosen, right? So each one will have equal probability that they are like the spicy food, right? For each single one, right, it will be a single person, right? Maybe 30% they like, right? And 70% they don't like, right? The question is, I asked 5 people, right? So what is the probability that 2 of them like? Okay, so how to calculate this probability? Okay, so this is exactly the binomial distribution, right? So that's why here we take n equal to 5, okay, and P is success. We call a success is like, right? So it's 0.3, okay, and x here is 2 because we want 2 success, okay? So that's why we have NCX P because it's NCX, right? P to the x, 1 minus P, N minus X. Okay? Is that okay for this one? Okay, I guess I have a lot of hard time to understand this when I was a student. It's very good that you understand. You don't have a problem. Okay, that's good. Okay, you got a problem, then I don't have anything to say. Okay. Then maybe we go to the proof. Okay. We're trying to show you the proof of the binomial. Okay. So here everything can be proved, but we just choose to prove something that I think that worth some effort of proving. Okay. So we are trying to prove that this is exactly this. Okay. Try to show you, and of course, some of you may worry we ask a proof in the exam. I guess probably not. We are not asking the proof in your test, but the thing is, you want to know why they're right? Because instead of telling you, at least you need to know some basic idea what's going on here. Okay, that's why we try to prove some of the statement. Okay, so we want to figure out the summation x times p of x. Okay, this is the key. Okay, and what we're going to do is replace this guy by its own definition. Is that okay for the first step? Okay. The next thing is x from 0. This is 0 times this guy. Okay. So you can start from 1. So that's what it changes here, right? Because there's no difference from 0. Okay. And the next thing that we will use a interesting property, actually can prove easily. X times NCX is equal to n times n minus 1 x minus 1. Okay. How to prove that? That is easy. X n cx is n factorial, x factorial, n minus x factorial. Okay. And you can x factorial and x cancel out. That gives you n factorial, x minus 1 factorial, n minus x factorial. Okay. And then you can take n out, become n minus 1 factorial, x minus 1 factorial, n minus x factorial. And the later one is n minus 1, n minus 1 c x minus 1. Okay? So that's how you can, from here, you get to here. Okay? So that's the changes. Okay? And this n is a constant, so we can take out. So that gives you this part. Okay? And the next thing we do is what we call rewriting. That's commonly we doing for the rest of the chapter is let y equal to x minus 1. Okay, let's make this transformation. Okay, and in this case, when x equal to 1, y equal to 0. So that's how we replace this. When x equal to n, y equal to n minus 1. That's why you have this summation at the top. Okay, and y equal to x minus 1, so that's why x minus 1 become y. Okay, and x will become y plus 1 because you just replace y plus 1 is x, right? And you do the same, x become y plus 1. Okay, and we have plus 1 here, take it out with np. Okay, and this n minus 1 y py n minus 1 y. So this is summing the probability distribution of binomial of n-1 p, right? And summation of all the probability will be equal to 1. So that's why this is 1. Okay? So that's why it's NP. Okay? Is it okay? Any question? No? Okay, that's fine. The next one we have is second moment. Okay. So as we remember, right, we give you the formula. Variance of x can be written as expected x squared, okay, and expected x whole square. Okay. We figure out this. We'll try to make our life easier to find this one first. Okay. This one turned out to be much easier to calculate. Okay, you can see the math is very similar to what we have in the previous slide. Okay. So expected x squared is x squared times p of x. Okay. And then you have just replace p of x by this guy. Okay. And then because starting from 0, you have x 0 times anything, finite, right? You can just start from x. Okay. And then use the same concept, use the you take because square here, right? So we can take x and take it out. So basically what I do is x, like the previous case, is equal to n minus 1 x minus 1. Okay, I just proved it before. Okay, I just take the n out. Is that okay for this one? So that's why we have this and this. So combine two steps together. Okay. And here I use the same trick again. I use y equal to x minus 1, okay? Or x equal to y plus 1. And I replace everything x to y. So that's why x become y plus 1. X minus 1 is y. X is become y plus 1. But this 1 comes out here. That's why it's p here. Okay, I just do some trick here. Okay, x equal to y plus 1. Okay, that's why everything replaced with a trick. Okay, and you have 1 here. Okay, I would put an out, and you can see this the same step as before. This is sum of the binomial n minus 1, so that's y is 1, so you don't have this thing here because this is 1. Okay, and what is left here is will be p of y times y, and again it's the same trick, right? And you have p squared and n minus 1, okay, and your z, okay, and the same trick here. This will become 1 again, okay. That's why n minus 1 p squared plus np. Okay, and is there any question for this one? Because we're just repeating the same trick. Oh, because this guy, why? Because this guy is binomial n minus 2p. So some of them is 1. So then that's much easier. Actually, same trick we have done before. Is it clear, poaching? just a mean. Because this guy is 1. So that's why we can rewrite NP n minus 1 p squared. So that's the idea. So same as what we've done before, but just a little bit more complicated. Just, I think time's up, but I will just one more slide, just prove the variance that we're done today. Okay. So the variance, okay. So we have, this is NP, right? And we have just shown this is M times M minus P squared minus NP. Okay. So we can see, right? Let's expand out. It's N squared P squared minus NP squared plus NP minus N squared P squared. So this cancel out. Okay. And then you can collect terms NP 1 minus P. Okay. So that's how you can prove this is the case. Okay. But if you remember our idea, variance of x, if x is equal to x1 plus x2 plus xn, right? If they are independent, okay, then you can write this variance of x1 plus variance of x2 plus variance of xn, right? A binomial actually sum of the binomial, right? And they're independent, right? Remember, for binomial, each is p times 1 minus p, right? We have p times 1 minus p, okay? So actually this, at the end, will give you n p times 1 minus p, okay? Doesn't come as no surprising to you, okay? So that's why, even though I proved that long, actually you don't need that, okay? You can just say, okay, because of this is a binomial is p times 1 minus p and they're independent, we can prove it, we're done. But we're just showing you that you can prove it directly or you can do it smartly, okay? Is that okay? So let's end here. Next class, we will continue for the rest. So I stay around to answer any question you might have. So remember, Thursday is mid-autumn, so happy mid-autumn, and so we will not have class. Okay, so we'll see you in October. So have a nice weekend and thank you. Bye-bye. Don't eat too much mooncake. Huh? Mooncake, have fun. No, quiz will not be great, don't worry. Quiz is just an attendance base, yes. Bye-bye. Yeah, have a nice mid-autumn. I stay around, answer any question you might have here.
Sorry. Can I ask a question
Yeah,
about
please.
the proof of the second moment?
Yes.
The third step to the fourth step.
This one.
Yeah.
Okay. You jump a little bit. So, but it's the same. So let's go over there again.
Yeah.
Here's 1. Okay.
Yeah.
So this guy, hopefully you can see the summation of this is 1, right? The summation of y equal to 0, n minus 1, n minus 1 y, py, 1 minus p, n minus 1 minus y. This is 1. Can you see that?
Okay.
This is 1, okay? So that's why np times 1, this is why np is here. Is that okay for this one first? Because this is the binomial.
Yes, you mean you separate with separate 1 and y.
Yeah. That's why np times 1, right? This np is here. Can you see this one first?
Okay.
This one okay, right?
Yeah.
And then this is gone, so that's why we can erase it because it's here. Okay.
Yeah.
The second step will be involving here y times n minus 1 y here, right?
Yeah.
You can rewrite this as n minus 1, n minus 2 y. Okay. Is that okay for this one?
Well, why will you z here?
Oh, let's wait. Let's be patient a bit. Is that okay first for this one?
So sorry. Why here is it?
I'm asking, is it okay for this? Is that one okay?
I
You can
think it's
prove it.
okay.
N minus 1 factorial, y factorial, n minus 1 minus y factorial, and y cancel out, give you y minus 1 factorial, n minus 1 minus y factorial, and n plus 1 taken out. This gives you the n minus, oh, sorry, it's n minus 2. So, sorry.
Yeah, I think no, I can understand. Yeah, let's.
Okay, then it's okay.
Yeah.
Then n minus 1 is a constant, can be taken out, that's why n minus 1 here.
Yeah.
Okay, and now we will have, let's write this part. Okay, let's write this part. So maybe I open the whiteboard. Let's see whether you can see my whiteboard. Let's see.
Yes.
You can see my whiteboard? Can you?
Yeah.
Is it you can see my whiteboard? You can see my drawing? No.
Probably no. Yes, it's totally. That's right.
Let me have a new share of the whiteboard. Can you see the whiteboard?
Are you writing? I cannot see what you are writing.
Can you see the whiteboard? Can you see the whiteboard? Can you see the whiteboard?
Yeah.
Good. So, so what I have is NP summation. I just copy the second step. Okay. Y plus 1 and n minus 1 y. I just copy the second step. Okay.
Yeah.
So the first thing, as I said, this one is gone, so there's NP here. Okay, and
yes.
NP y equal to 0 and minus 1, right? And remember, we have y times n minus 1. You said okay about this point, right? N minus 1 and n minus 2 y py. Is this part okay first?
Yes.
We just discussed this, okay? The next thing is take the n minus 1 out, right? So we have n minus 1, right? And then p and then n minus 1 summation y equal to 0. I just take n out, okay?
Yeah.
Okay. And what we do is now I have to replace y by z, okay?
Okay.
So what, okay? And am I right about this? Oh, wait a second. Also, this is y. So, so that's a step first. Y to 1, so I have to replace y equal to 1 first. So that's, sorry. That's a one step I miss it first. So this is y times n n minus 1 y, right? So y from 0, I can start from 1, right? There's no difference. Is that okay for this one?
Yes.
Okay. And here I have y equal from 1. And this case, I can replace this by saying z is equal to
Y minus
y,
1.
y minus 1. Okay.
Okay.
Then I will start when y is 1, z equal to 0, right? That's n minus 2. So I have n times. I just rewriting things, okay? Instead of counting y from 1 to n plus 1, I counting z from 0 to n minus 2, okay? And in this case, I have y so I have minus 1 here. I forgot it's y times y minus 1. So then there is y becomes z, okay? Is this part okay? Okay. And p will become, because y is z plus 1, right? Z plus 1. Okay. And I have n minus 2 minus y plus np. Is that okay for this one?
Yes.
And then this plus 1 can be taken out, right?
Yeah.
I become 2. And this is 1. Can you see this one is 1?
Yes. Yes.
So that's why that's what we got in at the end.
Okay.
Is that okay? Or you want me to explain which part? Because I think each step
I
is
think I already understand. Yes.
good. So if you still have questions, just I go step by step. Yeah.
So could you wait a minute, and I think I hope to write it down.
Oh yeah, sure. Don't worry. No hurry. Just take your time.
Yeah. Okay. Thank you.
Okay. Have a nice weekend. Enjoy
Yes,
the
thank you.
long weekend. I see you next Tuesday. So any further question, because I need to attend another section, the H section H. So if there's no question, I need to end the section. Any more question from Choya, Ninam, and Chimen? Anything I can help further? If no, then I have to end because it's almost time for the other section. Any question? Okay, then sorry I have to end it. I hope you have a nice weekend. See you next time.